So I chose this one because some interesting things happen with this graph. First of all, next to the 2/3 minus x, you can think about domain and range. There's no non-permissible values. You're never dividing by 0. So our domain is everything. If we would do some of the preliminary stuff, remember my color coding. Y-intercept, really easy. Plug in 0 for x, get 0 for y. X-intercept, a little bit more tricky here. What we could do is we could factor out, since we know that x is an intercept as well, we could factor out an x, leaving us with x to the negative 1/3 minus 1, and then we could set this equal to 0 and x equals 0, and we could set this equal to 0. Now if we set this equal to 0, initially if you look at that, you should feel like, ooh, I don't know how to solve that. That's because you don't normally solve things that look like this. However, it is something that has only mathematics that you've learned in the past. You know negative exponents, you know cube roots. So let's see, if we change this to things that we're more familiar with, what does it look like? So I could change the x to the negative 1/3 to the bottom and a cube root of x. I can move the 1 over. And if you're solving an equation with x on the bottom, you can multiply both sides. And then to get rid of a cube root, you could cube both sides. So none of the skills in that solving are anywhere out of what you've done in the past. However, I think that combination of putting them together should feel a little bit weird because you don't, like, this could be a grade 11 question, but we don't ask grade 11 questions quite like that, combining all of those ideas. When you see all of the steps, you realize, yeah, nothing there was that hard, but sometimes what a question originally looks like can throw you off, okay? A couple of things to note, just a couple of common mistakes that I keep seeing over and over again. With this x to the negative 1/3, it's just the x to the negative 1/3 that goes to the bottom. The 3 isn't affected by that exponent, but there's a temptation from a lot of students to move that 3 to the bottom of the fraction as well. So just to point that out. So we have an x-intercept of 0, 0, obviously, and we have another one at 27, 0. So there's preliminary stuff. This graph has no asymptotes, so now we can get into the derivative part. Is it using f of x or y? It's using y. So y prime bring the 2/3 out in front, subtract 1 from the exponent, minus 1. So when I brought the 2/3 out in front, the 3 multiplied by that 3 on the bottom, just leaving with a 2, subtract 1 from the exponent, set our derivative equal to 0, and again, this would be very similar to what we just did with the last one, right? We can move the 1 over, multiply, then both sides by that cube root, and we get x equals 8. Okay? But something to note that came up in this question is that at this point here, in our derivative, we do have a non-permissible value. That x can't equal 0. And this would be something that most students would miss when doing our number line. Students would put the number 8 on there for the derivative, but they would forget to put 0 on there, because it's a critical point. So we do all stationary points, and then all critical points. And critical points will include non-permissible values of the original graph, but also non-permissible values of your derivative graph. So this is why I added this to the notes. There's one like this in the homework as well. But pointing out this, because it's different. We haven't had questions that have had that very often. Now that we have these values, we can plug things in. And this one too is a little bit awkward for figuring out the derivative. If I plug a negative number in, okay, the cube root of a negative number is negative. So this fraction right here would be negative. Minus 1 would still be negative. So we know that our function is decreasing. Okay? Then, if we plug in between 0 and 8, I'm going to pick 1 because that's something I can do the cube root of. So cube root of 1 is 1, 2 over 1 is 2, 2 minus 1 is positive. This is increasing. And plugging in a number bigger than 8, like 10, or in this case I can plug in 27. Okay, if I plug in 27, I'm going to get 2/3 there. 2/3 minus 1 will be negative again, because as we get bigger and bigger for x, you can see that that first fraction will get closer to 0, and then when we subtract 1, we'll be in the negatives. Okay? So what do we know? We know that 8 comma something, we know that that's a max. But 0, 0 is not a max or a min. You might be tempted by looking at the graph to say, oh, it's a minimum. Look, goes down and up. No. Well, it might be a minimum. Okay, but it's not, we can't say that yet. There we go. Beautiful mathematical teaching here. We can't say it yet because our first derivative rule says something is a maximum or a minimum if the first derivative is equal to 0 at that point, but it was a non-permissible value. There was something different about that. I don't know. I almost feel like you should put like you could do this. We can make this up. If it's a non-permissible value, put a little circle at that point to remind yourself, hey, that point wasn't allowed for my derivative, or it wasn't allowed for my, so we don't get sucked into saying, oh, I think that's going to be a minimum or a maximum. We don't know yet, because it doesn't fit our rules. It's going to end up being a minimum, but we'll find that out later. Okay. If I want to find has anyone plugged this into their calculator yet? We could plug in 8 into the original equation. You get 4. Double check that work? Good mental math? Okay. All right, so we got 8 comma 4 as our max. Now, switching to purple. Purple is our second derivative. I'm going to take a look at my first derivative. 2x to the negative 1/3. The negative 1/3 would come out in front. Subtract 1 from the exponent. And then the derivative of 1 would be 0. So again, what does this mean? if we set this equal to 0, we would get negative 2 over 3, this x to the 4/3, that would be the cube root of an x to the 4. Move down to the bottom. Setting that equal to 0. If you multiply both sides by the bottom, you get the following. Interesting. When is 0 equal to negative 2? That's not possible. This has no solution. However, it also has a non-permissible value that x can't equal 0. So even though there's no solution to our second derivative, we can still make our second derivative line and plug in the non-permissible value, which I've now started to label with circles like that. I like that, I really do. Because that's not going to be an inflection point then. It's a non-permissible value. Usually our second derivative finds us inflection points. But this, well, I'll have to talk about definition of an inflection point a little bit here. Usually that would be what would make it an inflection point. We'll talk about it here. It's not necessarily one just because of what happened. Because there could be an asymptote there. We'd have to check when we get to our original graph, which is why I'm doing this one, because this is so odd and therefore interesting. So if I plug something into my second derivative before 0, I hope you can see that no matter what you plug in, because it's going to the power of 4, and then you're cube rooting it, it will be positive. So the bottom is always positive, so this will be negative. And this also will be negative. So for sure, it is not a inflection point because it's not changing concavity. Cool. Okay, so if we now look at everything that we have for our original graph, I'm going to mark 27 there, space it about the right way. I'm going to mark 8 about there. I'm going to mark 10 up here and 10 down here. So what did we find out? We found out that our x-intercepts were 0, 0, and 27, 0. We found out that we have a special point at 8, 4. And in fact, if we go up, here, just change our view so we don't have to skip. Oh, perfect. You can see that really well. If we look in our green, we found out that 8, 4 was a maximum. We know that our graph is going down until 0, then up, then down. And we know that the concavity before 0, the concavity everywhere is down. And one of the things I had mentioned from before is usually when you're graphing, you start from your inflection points. Or in this case, we have no inflection points, but we are still going to start at 0 and look at what happens there. Okay? I'm going to start with the easy part, which is to the right of 0, because I have points to the right of 0. So to the right of 0, this is what would have to happen for it to be concave down. In order for it to stay concave down, it would have to go through those points and look like that. Now, I need to be concave down on the right, or that's your left, the left side of 0 as well. I can't draw this. This would not be allowed. And the reason this would not be allowed, it's concave down, it seems to be okay, but it would introduce another x-intercept. And I found all the x-intercepts. So this part, in order to be concave down, would have to go like this. And if we imagine our original equation, what happens as x, you put in a very large negative number of x? Well, this would become a large negative number, but this would become minus a large negative number, adding a large negative number. If you think about doing limits, right, the limit as x goes to negative infinity of this original graph, we could factor out the highest power. That was our method, right? We also, in our limit, sort of an intuitive way, we just said, well, what's the highest degree? That would be that x to the 1. So if we just think about what happens to that x to the 1 as you go to negative infinity, it would go to negative infinity, but there's a negative out in front of it, meaning that it goes to positive infinity. And so it's concave down, but it keeps increasing in that direction. We can also see that this has to keep going up to the left from this part of our derivative.
You have a couple of pencils. Let's keep them.
Yeah, just look like mechanical or just regular?
Yeah, just regular is fine. Just got a couple laying around.
Yeah, for sure.
Go down to the office and get some. My spare.
I think I gave all my 4 enough.
Oh, that's fine. Thank you.
And so what we have, we zoom back into that graph that we drew. What we have here is a minimum, a local minimum. It would still be considered a local minimum, although it doesn't follow the minimum rules of the first derivative test. Okay? We call this a cusp, a sharp point. So this one was a sharp point that also happens to be a minimum. I was wondering, could I draw a cusp that's also an inflection point? Like, wow, there you go. Right? What happens if you had a piecewise function that went like this, concave down, and then went like this, concave up? Technically, you could get a sharp point there that has no derivative on that point, and then would be non-permissible value for both the first derivative and the second derivative, but does change concavity. I've never seen an actual equation that does that. I don't know what the purpose of me making one up would be, but other than thinking about it and saying that could be interesting. But this graph was interesting because its domain is still everything, but it has a sharp point in it. I guess the main ones that you've seen so far that have had a sharp point are absolute value graphs. Okay? But absolute value graphs are really just 2 lines put together. I'm like, you want to feel special, Mr. Absolute Value, but you're really just a piecewise function of 2 things put together. This graph is a legitimate graph on its own. It doesn't need to be written in 2 different pieces. It has its own equation, and yet it still has this weird point